Hi everyone. So I know I said I wasn't going to do a video this week, but this is just like an extra video to show you some really cool visuals that you can use as you're doing this 3D solids unit. So this is a website called GeoGebra, and I would actually be showing this to you if we were in the classroom right now. But I'm going to make a video instead and kind of geek out a little bit. So this is really cool. So we did prisms last week, and you might have struggled a little bit because it's kind of hard to figure out sometimes what all the different faces of a prism are. So if you don't have your fancy shapes like I do, GeoGebra is really cool because you can search any type of prism, and what it'll show you is actually the net of that prism. So for instance, I have a hexagonal prism, hexagonal, and I can actually see the net of this if I press this red button down here, and you'll see, look, it opens up, which is really cool. So I can see it put together, and then I can see it flat. And by seeing it flat, I now am able to see all the lateral faces as well as the two hexagons which make up the bases. So you can search anything on here really, and GeoGebra will show you its net. And it's really cool to play with. Then we have this one. So this is my triangular prism. It's a little different because this time I'm going to look at the cross sections of a prism. So for instance, I can move this up and down here, and you can see that the cross sections is just a bunch of triangles stacked on top of each other. I can rotate it if I want to see the different triangles at maybe an angle of the shape. I can rotate that way as well. And then what's really cool is I can actually view from the actual cross section. So now I can see what the triangle looks like. So this is really good if you ever needed this for your prisms. Now this week we're going to focus on pyramids. Now pyramids have a lot going on. If you remember, they have a slant height, which is really just the height of the lateral face. So that's why they're calling it lateral height here. And that slant height comes down, and it's perpendicular to the edge as well as it bisects the edge. So we really have a bunch of isosceles triangles, and the slant height acts as the median or the altitude. But the important thing to know is I need to know what's going on inside the shape. So if I slide up here on GeoGebra, this is cool. Now I can see that not only do I have my slant height, but I also have my what they're calling true height, or just the height of the solid, which starts at the vertex and is perpendicular to the base. And what I've created now is a right triangle. So you'll probably see on the notes I said look out for all those right triangles, because now you can use the Pythagorean theorem if you're missing anything. So maybe you need to find the lateral area of a pyramid, but you don't have the slant height. You could use the Pythagorean theorem in order to find the missing piece. So this is just a cool visual to help you with that. Another thing here is this goes back to the nets. So if you wanted to see the net of a pyramid and what makes it up, we know we name a pyramid based off its base. So you probably can see that this one's a square. So this is probably going to end up being a square pyramid. But I can actually fold it on up, and look how cool that is. It opens and closes, and you can see it as a net or all put together. This is probably my favorite thing on GeoGebra. And when I learned this, I think maybe high school, maybe I didn't even realize it until college, but the formula for the lateral area of a cylinder is 2 pi RH. Now you can memorize that, or if you know where it comes from, it makes it so much easier. So here I have my cylinder, and you can manipulate the height if you want to. So height is basically the pink here. And watch what happens when I open up this cylinder and look at its net. So you'll see the top opens. And what do you notice? Well, the lateral face of a cylinder is really just a rectangle. And the the cylinder's height is really just the width of the rectangle. So if I open this up and flatten it down, look what happens. Take note of the black circumference around the circle. It opens up, unfolds, and now that becomes the length of the rectangle. So why is the lateral area of a cylinder 2 pi RH? Because the circumference of a circle is 2 pi r. So that you can see the circumference is peeling off and forming the length, times the height, because that's the width. And then the formula for surface area is your 2 pi RH, which is the rectangle, plus 2 pi r squared, because pi r squared is your area for a circle. And you can actually make this bigger, manipulate it, but I always thought this was so cool that you could see where it really comes from, the formula. Oop. Then we have cones. So cones are cool because I can actually look at the net of this one. So this one actually opens up. Again, you can see how the circumference of the circle really just becomes the bottom part of the circle. So it kind of looks like a sector. So that's the net. This one actually shows us how the formula works. So the formula for the lateral area of a cone is pi r L. Now L is your slant height, R is your radius. So this is cool because I can flatten, I'm going to take the top of this cone, I'm going to flatten it down. And it kind of looks like the sector of a circle now. So originally, the circumference of this was 2 pi r. Now we're going to flatten it down. And we want to find the area. So you could actually create a proportion to do this, but this is cool. So if I show you all the different dissections, you can make as many as you want, and I rearrange them, look what ends up happening. It opens up, those pieces fold together, and now you've got your rectangle. And if I have less dissections, it's curved. But the more and more dissections I add, it becomes a straight line. And now I have this rectangle where the width is L. So that is pretty cool. That actually shows you how to find the lateral area of a cone. And then the lateral area plus the base gives us our formula pi RL plus pi r squared. So that one's pretty cool. And then last but not least, we've got our spheres. Let's see if my sphere will load. All right, so here's my sphere. So we are talking about surface area, and later we'll talk about volume, but this is cool. So you can see there's all these like little parallelograms going on. Now, if I was to take out a wedge of this sphere, look what actually a sphere is made up of. A bunch of pyramids all stacked together, and the pyramids all have different bases. And together, if we add up all those bases, that's how you get a partial surface area of the sphere. Add them all up, you get the total. So that's where, there's a whole proof of it over here, but that is where the surface area of the sphere comes from. So if you ever need a better visual of anything, as we're doing our last 2 units on surface area and volume, definitely go to GeoGebra, and I will link this for you. Alrighty, see you later.